All right, welcome to day 23 of Advent of Code 2024. I'm doing this day late, but let's just get started. So we're looking for triangles, okay. $3,000. If we do 3,000, choose 3, that's going to be a little bit slow, so probably not. Well, okay, shouldn't be too bad. Okay, we're going to make an adjacency matrix or list. And then we're going to go through every single computer in this list. We should go through every pair. Tuple sorted Aij. So that should be all the triangles. Okay, for A, B triangles, if T in A, B, C, or A0, B0, C0, and add 1 to the answer, and then print the answer. Okay. Dictionary size changed during iteration. Line 13. There should not be changing size. Zero. Okay. That's not good. Okay, I see what's going on. So we should be checking for all the neighbors here. Oh, yeah, 7. It's a little bit redundant, but I mean, it should solve the puzzle. So 893 is my answer. Okay, pretty good. Largest set of computers that are all connected to each other. Oh, wow. Okay, so we need to find the largest set of computers that are all connected. This is like a well-known problem. This is like a clique finding problem, where a clique is a set of nodes that are all connected to each other. Can we make use of the fact that we've already found all the triangles? I think a good place to start would be to look at the sizes of, or like the degree of every node. So find the max degree, and then I think that should be simpler. $13. Okay, so 13 isn't so bad. Because once you have this, you can verify that, you know, any subset is a click. Okay, 2 to the 13 should be totally doable. So you have a function to verify if something is a click. Basically just look through all pairs of nodes. Actually, that's probably redundant. So we just need to verify that everything is within everything else's adjacency list. And now we just need a way to generate all possible list of neighbors. Okay. So for every node, you get the neighbors, and then you iterate through all subsets of those. So you know, we're going to use iter tools because it's most convenient. Okay, so this is going to generate all length neighbors, length tuples of false and true. Okay. For I in if x, so if the value in the mask is true, then add that neighbor, and then if is click nodes, then ants equals max ants LAN nodes. Okay, that should be it. Let's import TQDM because this might take a while. There is some redundancy here, which shouldn't be too bad. Okay, 4 rates. Let's hope this works on the actual thing. Oh my. Okay. Okay, it's going to take about half a minute to run, which is a little bit inefficient, but it's okay. I'll try to optimize this code a little bit. We can make it run like twice as fast by doing this. And then we can also turn this into a set to make checking for inclusion faster. Oh, set is not subscriptable. Line 30. Neighbors. Oh. Okay, you know what? We're going to ignore that optimization. That should run... Okay, it doesn't run that much faster. I thought it'd be twice as fast, but it's okay. 13. Oh, I didn't print out... Okay, it didn't print out the biggest click, which is okay. So if line nodes greater than ends, or actually we just big click, and then we just print out the answer. Okay, so this is take about half a minute to run. Whew. Okay. Let's see if this is correct. All right. Awesome. Day 23. Okay, so for today's puzzles, we are working with a graph of computers. All of these computers have a 2-letter ID, and the input gives edges in this format. So it gives you the first computer, second computer, separated by a, I guess, hyphen. And our goal is to find all the triangles in this graph. So a triangle is any set of 3 computers that are all pairwise connected, and it's an undirected graph, so we don't need to worry about arrows or anything. The goal is to find all triangles that contain a computer that starts with the letter T, and there could be multiple, and we need to find out how many of those triangles there are. So finding triangles itself is not too difficult. To parse through the input, we just go through all the lines and then split by hyphens, and then we create an adjacency list, which tells us for every single computer which computers it's connected to. And then we just go through all of the computers in this iteration, this for loop. For every computer, we check all pairs of computers in its adjacency list, because that, allows us to check whether those 2 computers are connected. And if so, then we can add it to the list of triangles. And then at the end, we just check which triangles have a T in the first letter of any computer, and that's our answer for part 1. For part 2, we need to find not just triangles, but clicks. A click in a graph is any set of nodes that are all pairwise connected. So it could be bigger than 3. In the given example, it's 4. So there are 6 edges in that click. And we just need to find the size of the biggest click, find the IDs of the computers in that click, and then join the IDs with commas. So how we do this is I wrote a little function to detect whether a set of nodes is a click. And to do that, you just go through all pairs of nodes in the purported click and check if they're connected. If any of them are not connected, then you return false. But if none of that happens, then you can return true, because all of the pairs of computers in that click are actually connected. Now, to generate all candidate clicks, we can narrow down the list. Instead of going through all subsets of computers, because that would take way too long, we can look at every node and then look at all the neighbors. I did a check at the beginning, which tells us that every node is only connected to at most 13 computers. Turns out that is the size of the largest click, which is pretty cool. So 2 to the 13 is not that big, which means for every node, we can afford to go through all subsets of its neighbors and check if the central node plus the subset of those neighbors forms a click. And that's what we do over here using itertools. Itertools is my favorite standard library, probably. We can generate all subsets by looking through the list of neighbors and then generating a mask, rather several masks. So 2 to the power of number of neighbors. That's the number of masks we generate using this product method. And then we have a list here, which we are going to fill with the nodes that correspond to true in the mask. And then we have our purported click. We check if that's actually a click using our function. And if it is, then we can update the biggest click if our found click is bigger than the size of the current biggest. At the end, we can print the length and also join the answer with commas. This took about half a minute to run, which is not too bad. But I'm sure there's some optimizations that could be made. So that's it for day 23 of Advent of Code 2024. Hope you enjoyed the video. Thanks for watching, and I'll see you for a future day.